So we are continuing studying covering spaces and what is the role played by fundamental group. So yeah, so as promised, we want to show the following. We want to show some proposition about existence of a universal cover. Assume, so the statement is the following: assume Sx is path connected. Then we want to require some other technical conditions locally. Want it to be locally path connected. So this is a notion which we introduced last time. So this means that for any there is an arbitrary small neighborhood, for any point there is an arbitrary small neighborhood, open neighborhood, which is path connected. But we also want to introduce another condition. We want X to be what is called semi-locally. Simply connect. So I will define it in a moment. Anyway, this is some technical condition, and so this is actually will be a necessary condition as well. So we have to require it. So if the condition satisfies, there exists X tilde covering X, so its fundamental group stereo. That is, so if you remember the definition which we made last time, this means that by definition X tilde is a universal cover.
Is it P1 of X tilde?
Yes. Okay. Let me. What is the definition of this locally simply connectedness? So, from the topological space. Let's say Y is semi-locally simply connected. If for any it's a local property, it's a property about neighborhoods of any point. If for any point X, sorry, let's use Y first. Y, there exists a neighborhood containing this point and then put inside Y, such that if we consider the map between the map from the fundamental group of this neighborhood to the fundamental group of the whole space, the map which is induced by inclusion this map is trivial. Meaning it's a trivial homomorphism. So the image means that the image is trivial. So in principle, one can also define what is called just without semi, the definition without semi, which we are not going to really need. If the definition of locally simply connected is just there exists a neighborhood which is simply connected. But this is a weaker, you can see this is a weaker condition. So the simply connected would require just this to be trivial. But what we do, we don't require this to be trivial, we just require that the image of pi1 inside the ambient space is trivial. That's why.
Can we have an example of topological space which is semi-locally simply connected but not locally simply connected?
Yes. So I want to let me so example. This is y is so one can see the example where y is locally simply connected. So we want to get to the example which is semi-locally connected, but not locally. So locally simply connected would mean just any neighborhood has a any neighborhood has simply connected. Simply connected. Any point has a simply connected neighborhood. So let me do the following. So let me start with the first topological space Z. Z will be, if you're familiar with this notion of example of Hawaiian rings. So what you do is consider union of well, these characters and words. So union of circles in arc2 with radius, let's say radius 1 over n. So the union will be from all n from 1 to infinity and centered at, let's see. So we want them to have just a single common point, all of them. So they center it, if we take the radius and they center it at 0 axis. Center it at 0 and 1 over n, right? So some infinite, we start with this space. And then I consider y to be what is called home over z. So you can assume this is z times, so I take a cylinder first, so I just multiply z by an interval, and then I make a quotient for the all points. I collapse all points which are in Z times 0. So you can visualize something like this. You have a cone of this stuff and make a cone, which is essentially unions of cones over each subcone. And you can see that if I take, for example, like the point, consider point here. So for any point here, the neighborhood will look like essentially some small interval. Any neighborhood will contain the infinite number of circles intersecting at one point times open interval. Right? And this is, of course, it's homotopic just to the infinite number of circles. So this is definitely not locally simply connected, because any neighborhood of this point contains infinite number of circles, and we know the circles are not simply connected. But it's semi-locally simply connected, because if all these loops which I can draw here, since I can if I embed them. So even they are in the small neighborhood here, when I consider them as loops in the ambient space, I can always collapse them. I can always contract them to this point. So this is why this map. Although this is not trivial for any neighborhood, this map is always. So let me make the following remark that so this is being semi-locally simply connected is actually the necessary condition. If X tilde is universal cover, that exists, which is the universal cover. Then it follows that X is locally simply well, this is essentially, it's easy to see because if I I'm not going to do for long talk here. Let me just explain it briefly. So if I take, so we know that if I take some loop, some neighborhood, some point here, and I take a loop in this neighborhood, it's U, X. So we know that we can lift this loop to some loop here, and so we know that the so we know that this is simply connected. So the image so what I want to say is that yeah, so I can take, the point is I can take this neighborhood to be sufficiently small so that it's evenly covered. And, well, in particular, I can take some intersection of this neighborhood and an evenly covered open neighborhood. So, which is still will be, because the composite, this still should satisfy this condition. And since there is a homomorphism, if this U is evenly covered, there is a homomorphism to a certain open neighborhood here, so you can lift, so this small loop inside this neighborhood is lifted to a loop here. But we know that I can also, if I know that this loop is contractible in X tilde because X tilde is simple, because X tilde is simply connected. But then I just use this composition of this homotopy which contracts this loop, this projection to contract this loop. So this will give me a contradiction. Anyway, this is just a small remark. I mean, in our proposition, we will use this as a part of the sufficient condition on X. But we also require some extra condition. We don't just require X to be semi-locally significant, we also require it to be path connected and and locally path connected. So I want to prove this proposition about existence of universal cover. And so it will be a bit technical, but let me give you, let me first start with the idea. So the idea is the following. So let me fix some base point in X tilde. I mean, suppose we found a universal cover. I can fix some base point, and the fact that X tilde is simply connected as we know means that there, so for any point X tilde in X tilde there exists a unique path homotopy class of paths from X tilde X from my base point to X tilde. Since there is a as you know, the fact, the definition of simply connectedness is equivalent to condition that any, if I fix 2 points, there is the all paths are homotopic to each other. And we also know that we can, there's a way to obtain, so there's one correspondence to points. We found that there is a one for one correspondence between points like tilde and path homotopy classes of paths in X tilde, right? And we also know that the paths, we can construct paths in X tilde by lifting paths in X. gives us the idea that we can try to define the points of X tilde as just homotopy classes of paths in X. So, okay, this was an idea, so now we start a formal proof. So let us, again, according to this, let us define a set. So far just to define it. We define X tilde as a set, but later we will need to equip it with topology and other things. So let me define X tilde as a path homotopy of paths F in X such that they start at X0. And end somewhere. And the covering space for us will be then the following. The covering map will be the following. So the class of a path, we just associate its endpoint. Indeed, this agrees with this picture. Path F, so F1, and this lifted. And this point is essentially understood as a class of this path. Okay. Okay, so this defines just a set, but we need to check different things. We need to check that this is this topology shows that P is a continuous map and it is the covering map, and we need to check that this is indeed simply connected. So there's a lot of things to do. So we'll do this. So in particular, we need to define topology X tilde. Okay, so we'll do this in steps. So first, by making several observations and then using them. So let me define the following collection of sets. To the paths connected open sets in X such that the map is the homomorphism between the fundamental group of U and X induced by inclusion is trivial. And so we want to show that first we want to show that U is a base for the topology X. So not just all, because here we consider not just open sets in X, but open sets satisfying particular constraint. But we want to show that still it's those guys form a base for the topology in X. So to show that this is a base of topology, we need to show that any, if you take any open set, it can be covered by elements, by sets in U, particularly any neighborhood. So if I take V, let's say included with some map G, certain G, in U, and I take open V to be open subset in U, and I'll take for it to be path connected. This implies that V is also an element of U, because since composition, if I take a composition by 1 V to by 1 of U, and then to by 1 X, this will be trivial, because this composition is trivial because just this map is trivial. But this composition is the same as push forward induced by direct inclusion of V into X. So this means indeed the V is also an element here. Satisfies both of all these conditions, and this indeed it shows that any, so for any, if I take any point in let's say some open in X, which is some open subset in X, there exists V such that it contains V and inside Y. Because so this we use a condition because the X is locally path connected, and semi-locally. And semi-locally symmetric. For U is indeed a base.
Question. In the definition of X tilde, what is the classes?
So the equivalence class is for path homotopy of path F. So I consider some path in X that which starts from X0 and ends at some point. We don't fix the endpoint. Yes, I mean, but the classes are for fixed a path homotopy class. So we consider for fixed the homotopy which fixes the endpoint, whatever it is the endpoint of my class. So equivalence classes only allows me to deform paths like this.
So true map cannot be in the same classes if they don't have at least the same endpoint also.
Yes. But like in X, they can be different. Like for the same point, they can be different classes because this is not simply connected in general. But this is other questions? So here, I mean, the idea is that if you take some arbitrary, you can take arbitrary small because of this locally path connected. You can take always arbitrary small neighborhood, and this such that it contains, in particular, contains in Y, and it's path connected. And we also want to take, since it's we also know there exists a neighborhood, not actually open, such that the induced map is trivial. We can always take a smaller neighborhood. If you take a smaller neighborhood, it also satisfies this condition because this induced map is trivial. So this is the first step. So the other thing which you want to do, and so consider f to be a point in X tilde, which is a path homotopy class of a path in X with fixed starting point, and consider it's such that the endpoint is inside a certain open set in this collection U. And then we can define the following set. U. So it's a set constructed by a pair of an open set in X that defines this condition and the class F, like this, and it will be it was the following so the set of the following classes of paths. So we pass in X, which is a path in X, which are obtained by composing paths F, which we had before, with an arbitrary path, which is a path in U inside of X, and such that. So of course, in order to do this composition, we will define that H of 0 should be the same as F of 1. So this can be, since it is some sort of elements here are paths in X, homotopy class of paths in X, this is a subset in X tilde. So essentially we want to use these guys to construct a topology on X tilde. We also want to show that these guys are enter in the preimage of evenly covered neighborhoods. So in particular, let me first show the following property. So if I consider the restriction of P, or map which we defined before, so it will be a restriction. So it's the map from this subset to U. We know that the image is in U because the image, this map P just by taking the endpoints of the passes here, and we know that the end by construction the endpoint will be in U because the whole pass H is inside U. And so indeed the image is here, but moreover we actually want to show that this is a bijection. And first we want to show that it's surjective. And this is indeed the case because U is path connected. U is path connected, so for any there exists for any point here there exists a path H which ends at this point, and it's also injective. So this is because so U was satisfies the conditions that this induced map is trivial. And this means that all paths H are homotopic in X. If you fix F and a fixed endpoint of H here, H of 1, this class is always be the same as a class of paths in X, and this means there is a unique unique class here. So it follows that this restriction of P is a bijection. So later we of course want to show that this is not just bijection, but this is a homomorphism. But first we have to define the topology. Still there? Another observation which you want to make is the following: that take, again, we constructed these sets in X tilde, which are labeled by pairs of open sets in X satisfying certain conditions, and path homotopy classes of paths in X. We want to show the following: that those two sets are the same, actually the same. So the sets as the subsets X tilde. If whenever this class, which is an element of X tilde, belongs to this set. So how do we show this? How we show this is that, well, let me take, in order to compare these two sets, let me just take, first I take some element here and show it, just show that it also belongs to this guy. And then I do the other way around. I take some element here and show that it belongs here. And, okay, so if I take, so let me take some element here. So this element will be of the following by definition of this QF. It will be pass homotopy class of the following composition, where I require the image of G to be inside U. Right? So the definition of this thing. But I can rewrite this class as the class of the following composition. So we know that f prime, from this condition, we know that f prime belongs here, so it can be decomposed in this way. hf times h, where this is a pass also in U. And of course, I can, if I put my parentheses like this, this gives me, since both the image of G and image of H is in U, this gives me some element of the other set. Now I want to do the other way around. If I take some, consider element, an arbitrary element from this set, and so this is it will be of the following form. Again, the image of this path is entirely in U, and again I can rewrite it in this way, where the image, using the relation between f and f prime. Sorry, what I want to say. No, here, I'm just inserting h and h bar, where h, image of h is in U, and then I use the formula. This is f prime, and this is also an element in this set here. So I show that these sets are the same. Now we actually want to show, so we did some preparation, now we want to show that the collection of all open sets like this, so again they're paired by labels U and F in the class of F, form a base for topology. It's up to us how to define a topology on X, but if you want to define a topology using a base, not any collection of sets can be forms a base. So the collection, so if you probably know in your course of general topology, there is a condition on a collection of sets to be a base for some topology. There's a condition that for any, to remind you, so the condition that if you take two pair of elements in this collection, at any point in the intersection, there should be a third element in this collection which is includes this point and contains in the intersection. This is what we want to check. Okay. So this is. So let me take some element in X tilde which belongs to an intersection of a pair of sets in this collection. So one set will be labeled by pair UF and the other will be paired by an element V and F prime. So both V and U are in our collection. So they both. I remind you, this means that they are open, they are path connected, and their push forward of their inclusion is trivial. Okay, so just from the previous statement, from the previous point, it follows that so since this guy belongs to this guy in particular, this means that U associated to F double prime is the same as U labeled by F, right? And we also know that we also know that V of double prime is the same as V of F. Just using twice this statement. Okay. And so we already know that this is a base of topology. This curly U is a base of topology in X. So there exists, in particular, it follows that there exists V W in U such that it contains F double U prime, F double prime of 1. So F double, the end of path F double prime is by definition should be in this. Sorry, what I mean is the W is in such that W contains this point, and the W is in the intersection. So we know because of this, well, the end point of F W prime is both in U and in V. So then I can take a set here which is associated with W and class of FW prime. By construction it will be inside this intersection. Which follows from this condition. And because I mean here we're considering composition of F prime, F double prime is path contained completely in W, but of course this means that they are both contained completely in U and completely in V. But now we use these equalities like before. So this means this intersection is the same as the intersection of U F and V F prime. Let's follow that this U, this is U F is indeed a base. Because we show what we did, so it's 20 point in the intersection of arbitrary pair of sets in this collection. We show that there exists a third. Sorry, this is not W here. So this is this guy belongs to this big collection, such that it contains it of course contains this class because of this condition, and it's also inside this intersection. Questions? So this equips Algebraic topology. So now we want to check that the covering map, which we define, we define the covering, the P just as a map between sets, but we want to show that this satisfies the condition on the covering map. In particular, I want to show that this restriction is a homeomorphism. So how do we show this? So if I take any, so now we know that these sets of this form, they form a base of topology, and still we take any open set inside this guy, this follows that, you know that it follows that its image is V, which is inside you. And this is because well, the P acts just by taking endpoints of classes, of homotopy classes here, which is by definition of this guy and the points in V. So we know that also we know that P is bijection. That this means that if I consider well the inverse of V, so this is called the inverse of P on V restricted. Well, this just means the restriction to this subset where it's bijection. We know that this is because this restriction, we already showed that this restriction is a bijection. You know it must be this set itself. So, which is an open set. So it shows that the preimage is any the preimage of any element of any V, which is inside inside this base, the element of a base of topology in X, the image is open. And also the image is also open. The image of an open set is also open. And now this is a projection, and both P and its inverse are continuous maps. And this implies that the P inverse are continuous, or the restriction. Continuous. This means that P is indeed homomorphism. And it also, well, you can do this for any neighborhood. For any point, and this implies that the whole P is continuous now. This is a P was a one from X to X. And well, we also want to show that this satisfies the property of the covering map. So in particular, so if you consider the preimage of U, we want it to be a disjoint union. To show this disjoint union of open sets of this form. Meaning, meaning that in this union, the elements here are either the same or they do not intersect. And so we know that because of the property we showed before, we know that if there is some element which belongs to both of these guys, they are, if X still belongs to both of these guys, then they are actually the same. Alternatively, if there is no element which belongs to both of them, this means they do not intersect. So indeed, P is a covering map. Okay, so what we did so far, we constructed. So we constructed X tilde as just as a set of some equivalence classes. And then we, after some work, we equipped X with topology, X tilde with topology, and now we showed that this map P is indeed satisfies all the properties of the covering map. So far we constructed a certain cover of X. But we want to show this is simply connected. To show that it's simply connected. Logical space.
A question.
Yes.
We define this X tilde by fixing one point X0.
Yes.
And in this, when we want to verify that it's indeed a covering space, we have to choose any point. But this U is like, it's just a neighborhood of X0.
No, we consider it, well, this was a part, we use the fact that X is these are not neighborhoods of X0. This was a neighborhoods, so we consider it, so we consider we have X, so fix X0 point, then we consider it pass from well, we consider some paths F's and to F1. So U those U's was neighborhoods of F1. And this was what we denoted by U F was a neighborhood in X tilde, which is, we show that this is, well, there was a collection of neighborhoods because they can be different. Well, it depends because there can be many of them because for a fixed endpoint here there can be different homotopy classes. And the different homotopy classes, so for fixed different homotopy classes of paths from x0 to this point of f of 1 give me different different open sets here. And we show that each of them is homomorphic to U. Oh, by definition, this is a neighborhood of any point because any point is realized. This point here is a class of F. So this was construction for any point, the neighborhood of any point next. So I mean, like if I take some path which is not some path G, which has the same endpoint, and but is not homotopic to F and X, this gives me another a different open set here. They're both homomorphic to U, as we showed, but they are not. They do not intersect. And as a reminder, the neighborhood here. These neighborhoods were constructed by considering points here and plus the points here. Which is, and we use here, we use the fact that this is a U can be chosen to be path connected, and because of this locally sigma connectedness, there is no contradiction of doing this, of defining this. Questions? First, we want to show that X tilde is path connected. And so we need to show that there exists a path. If I take any point in X tilde, there exists a path between a certain base point, some other fixed point in X tilde. And so let me fix base point X tilde, X0 tilde in the class of a constant path in X. In X. So this corresponds just a path staying at this point. It doesn't go anywhere. And okay, so I need to show that there is a for any other point in X, still there exists a path connected those 2 points, and so there exists a path of tilde in X tilde from this class to this class. So indeed, So I can take, so I need to define, I can just define this path by formula. So the, what is the value of the corresponding map or S, where S is an element of a unit interval. And because again, I can understand this is a map. Still there. So the points here in X tilde, so for a fixed value of S, this will be some point in X tilde. So this will be some class of a path in X. Some class of paths labeled by S, where Fs is the following, so it's path in X, which is defined as follows. So I just define it. Well, let me take T equals to F S T. So indeed we can see that it starts from so 0 is mapped to f of 0, which is x0. It doesn't depend on S. Sorry, what? Sorry. And 1 is mapped to f of and then it's also if I take, so it's some path, so this is some path in X, but this is so we want to pass in X tilde. So we want to check, so this is some path in X tilde. So we have to check what is the start point of this path is F tilde of 0, which is a class of F0. So when F0 is when S is here 0, so this is indeed a constant. This becomes a constant path staying at x0. And F tilde of 1 is a class of f of 1. So f of 1, if I plug S to be 1 here, I get f of t. So this is the same as f of 1 is the same as f. So indeed I get f tilde is a path from this to this. And now I want to show that X is simply connected.
Why is this SF continuous?
Why is this continuous? Well, you can let's see. So if I take I want to show that, well, if I take, so let me, if I consider and the smallest follows that it's just given by this composition of continuous functions. And if you want to be more careful, so if f tilde, if I take some point f tilde of s, some s, and it's suppose it's inside constant point inside the following open neighborhood. And then I can just well, I can use the fact that if I so if I take consider well, take some. So I want to take some neighborhood. Z such that it contains S, and then says that f of S is inside just f of S, which is so f was a plus in X is inside U, and so this follows from the continuous from the continuity of the original function. But then since U is bijective to U of f of S, we know that the whole for the and this is a so this is a path connected. We know that the whole so we know that f tilde. So we know so here we know that the image of the z is contained in U. Then it follows that the image of z and f tilde is contained in U. Questions? Oh, sorry, I wanted to show you this. I wanted to show you X tilde is significant. In particular, this means by one of X tilde with the base point we chose to be a classical constant. Oop. Yeah. So we know that this is equivalent to condition that the image of because we know that P star is injective in general, so we want this is the same condition that this is a trivial subgroup. Trivial subgroup in phi 1. Okay, so what is it? This is the image. This image of P star. So what is this? So just using the definition of P star. So it's so we know and before we found we know the description of the elements in the image. It's a classes in P1 of X such that they are lifted to loops in X tilde. So they lifted. So this means the lift of F, which is a pass in general from pass in X tilde, is actually a loop. This means that its endpoint is the same as the starting point. At the starting point, we know this is a class of a constant loop. And, so what does this condition means? This condition means is the following. So so we can start in the previous point. We can start the lift. The lift, essentially the lift of a pass, and so we know. So basically we know that the so what I want to say here is the following. So yeah. So yeah, the image. So yeah, in various point we can start the lift of a pass, and so F tilde of 1 was a class F of 1, F1 in the previous construction. And we knew that this is the same as class of F. So F here is a so the class of F here, since F is a loop, represents an element in the fundamental loop. So this becomes just a statement as the class of F is the same as the class of constant. Class of the constant loop. By the definition, this is a trivial element. It's the identity by one. It's just a statement that we only consider the trivial elements. This finishes the proof. Questions?
I don't understand well why the image of P star is this set.
You mean this?
Yes.
Well, let's see. I mean, so in general, the general definition. I mean, the general property of the image which we showed before, we showed that the image P star is so classes of loops in X such that they are lifted. They lift. So F tilde lifts is a path in X tilde lifting F. And the criterion for which when the elements in pi 1 are in the image, the criterion is that if I take this lifting, if I take a lift of F starting at X0 tilde, so we know this is a unique lift. If I fix the starting point, unique lift for us, then we want a condition that the endpoint is the same, the endpoint of the lift actually coincides with the starting. And here, if we construct the lift, so the lift constructed was constructed in the previous one. We know that its endpoint is a class of F itself. So the class and the start point is a class of trivial of a constant. So this condition, this general condition, becomes just a condition that this class F is trivial. So this is X here. And this is our X0. So this was a bit, yeah, I mean, this construction was rather abstract, but I mean, in many cases you can just, I mean, you don't usually use this construction to, if you want to find some universal color, I mean, usually, I mean, in many cases you can just guess what it's this is just a theorem which proves in general this. So maybe I can give you a very simple example of a universal color. Let me again, as in the previous example, let me take X to be C star, so it's a punctuate complex plane. And I want to show that X tilde, which is just C, universally covers X. So of course this satisfies the simply connectedness condition. Because this is just a homotopic equivalent point. And so this is so this is C, and the map is the covering map is just divided by taking an exponent. And so this is indeed a covering map because this derivative is not zero for z. So I can always find the I can always find the neighborhood. So for current mark, we require that it should be a local homomorphism. So you can always locally inverse our function. And this is true because the derivative is exponential, it doesn't vanish everywhere. The local inverse is of course given by the model. But we have to, so we can only inverse on some branch, not locally, because we have to fix a branch of the logarithm. So the different branches of logarithm discuss not different sheets. For fixed branch. Of course, I mean, we cannot take the log here. We have a C star, so the logarithm has a is not defined when this is zero, which is excluded.